And so today I'd like to talk about something called universal gravitation. As you all know, that gravity exists between the Earth and ourselves, which is the primary reason why we are still on the Earth. However, what I'd like to talk about here is this universal part of this gravitation. We know what gravity is. It's the force that keeps us, it's the attraction between us and the Earth. But this universal part, now that's interesting here. What this universal area means is that the universal here essentially means that gravity exists between all bodies and not just between the Earth and ourselves. Cells. This is an important concept right here, which is actually probably going to make, I'm going to add this, change that to yellow. That doesn't show it very well. But the gravity exists between all bodies, not just between us and the Earth. So let's come up with this. We had a guy, his name was Sir Isaac Newton. So we'll draw Mr. Newton right here. There's a crude drawing. There's his wing. Now the common story that everyone knows is that there was a tree, and it had some apples in it. And one day this apple fell and hit Mr. Newton in the head. Now, this story, although being very comedic, may not have actually been true. However, it may have actually stemmed from something much larger. So, I'm going to go ahead now and erase this drawing. Okay. What actually might have happened was that Mr. Newton, although it's true that he was hit in the apple, it wasn't exactly the apple that inspired this idea of gravity. What it really was the study of some things up here. We had the moon up here. We had, some stars all around the area there. Maybe a comet or two streaking along the skies there. So what actually happened was Newton was studying these celestial bodies, and an apple hit him on the head. And up until this point, he could not figure out why these celestial bodies up here were rotating around the Earth. So, when this apple hit his head, it inspired the idea that if the gravity could reach to the tops of these trees, then maybe gravity could reach all the way up to these celestial bodies. So, that's the history lesson on how that gravity came about there. Okay. Next up, we got a little bit an equation that we have here. So I'm gonna go ahead and erase this part here. Oh, wrong color. Okay. And instead, I'm going to replace it with this very long mathematical equation. So this right here is a mega equation. It says F of G, that's the force of gravity, is equal to the gravitational constant, the universal gravitational constant, times mass 1 times mass 2 divided by the square of the radius. So let's talk about each one of these. Let's talk first about the two masses, because this is the easiest. Well, if I have myself and the Earth, notice how much larger I am than the Earth. I apologize for that. So, you know, there's the African continent. There's maybe Europe. Down there. Okay, that's the Earth. Now, it's very simple here. This is mass 1, and this is mass 2. Or you can call this one mass 1 and this one mass 2. Really, it doesn't matter since it's multiplication, and the commutative property of multiplication states that you can multiply them anyway. So it doesn't really matter which one you call mass 1 and mass 2. Now r squared. Now there's a common misconception. Let's say I were to again draw these two bodies here. This one here, we'll call it mass 1, and this one here is mass 2. Mass 2. Okay. Many people think that r is this distance here. This is r. But that is not the case. That is not the case. Rather, the distance between these two bodies, the r, or should I say, is actually the distance from the centers of the two masses. That is r. Oops. Okay, let's try that again. This distance between the two masses, that is r. Okay, so we covered our masses, we covered r squared. Now what is this g? Now, g, as some people might think, they might think that g is 9.8, or I should probably say negative 9.8 meters per second squared. Meters per second, and then we'll just put a little squared sign right there. But that is not equal. That is not equal to g. Whoop, that's an e. Try that again. That is not equal to g. G is equal to. I'm gonna erase this actually. Right here. Oh. Equation. Okay. G is equal to 0.06, or no, I'm sorry, 6.673 multiplied by 10 raised to the power of negative 11. So that is G. So that implies that the force of gravity is equal to 6.63 times 10 to the negative 11 times the two masses divided by the distance between the centers of the two masses squared. And we'll go into a little bit more detail of exactly how you'd use this. Maybe I'll do a couple videos on possibly some practice problems here. But there are a lot of misconceptions around this idea right here. So this, if you take away anything here, it would definitely be that this formula right here is very important. I'm going to highlight that in yellow. Okay, well, thank you very much. See you next time.